In this lecture, I will discuss exact equations. In order to solve those equations, we first have a quick review of Calculus 3 about partial derivatives. So let psi be a function of two variables x and y. Then in Calculus 3, we denote partial psi, partial x, is the derivative with respect to x treating y as a constant. And similarly, we have partial psi, partial y. This is derivative with respect to y, and in this case, we are treating x as a constant. Now in your Calculus 3, I'm not sure if you have seen this, but we will need the notion of the so-called total differential denoted by d of psi. This is just partial psi, partial x dx plus partial psi, partial y dy. This expression is called the total differential of psi. So this quantity, total differential of psi, will be important for our topic here, and it's come from the fact that if the total differential d psi equals 0, then psi is a constant. Then there exists a constant c for which psi equals to 0. Sorry, psi equal to c. So what's going on is that in this topic, we will try to write a given differential equation in terms of a total differential d psi for some function psi. And if we can do that, then the solution to our differential equation will be just psi equals to a constant c. And if we are given initial condition, then we can determine the value of c. So now let's go to first order differential equation. Consider a first order ODE. As usual, we will have the equation given in the form of y prime equals to, say, an expression in x and y. So f of x, y for some function f. We will rewrite the ODE in the the format that mxy dx plus nxy dy equals 0. So to do this, the idea is to replace y prime here by dy dx, and usually f of xy will be a certain portion. We can cross multiply and rewrite the ODE in this format right here. Now this is not necessarily a separable equation, but we try to write this in this format first. And this format is called the differential form of the differential equation. Is called the differential form of the ODE. So you see that this differential form has the same format as the total differential, because for total differential we have a certain partial derivative of psi here, dx, and then partial derivative of psi here, dy. And our format very similar. A quantity m dx and then a quantity n dy. So the idea is, given the differential form of the ODE, we want to recognize the left hand side as a total differential of a function. However, in general, we may not be able to do so. So if we can find a function psi of two variables x, y, such that the left hand side of the ODE is exactly total differential d psi, then the equation is called the exact equation. So in order to have such a function psi, the equation must be an exact equation for this to happen. We will learn what condition to check for exact equation later on when they say a definition. So how does this happen? So if we want the left hand side of the equation to be exactly d psi, then recall that d psi, the total differential, is partial psi partial x dx plus partial psi partial y dy. That's the total differential. So if we wanted this to match exactly what the right hand side of the equation, what is the right hand side? M dx plus n dy. This is the right hand side of the equation. Now I dropped the variable xy, but keep in mind that m depends on x and y, n also depends on x and y. But for simplicity, I just drop those. So in order for the total differential to match exactly what mx plus m dx plus n dy, we must have m here should be the same as partial psi partial x, and n should be the same as partial psi partial y. Okay. So how or when this can happen? M is partial psi partial x and n is partial psi partial y. In order to check when such a psi exists, we'll recall we will use a fact from calculus 3. So look at the above equation. First, m equals to partial psi partial x. What happens if we take partial m partial y? Then we get partial square psi and then partial y partial x. So we take the derivative of psi 2 times. The first times in x, the second times in y. Similarly, if we take partial n partial x, then it's like taking partial derivative of psi twice. The first is in y and then in x. But recall from calculus 3 that for reasonable function psi, the two mixed partial derivatives should be the same. So mixed partial derivatives are the same. So what it means is if we take partial derivative of psi in y and then in x, it should be the same as partial derivative of psi in x and then in y. So the order does not matter. As a consequence, we must have partial m partial y equals to partial n partial x. And this will be the criteria to check for exact equation. And once we have the criteria, once we check that the equation is exact, then we can solve the equation by finding the function side from these two equations. Partial psi partial x is the same as m, partial psi partial y is the same as n. So let me summarize the theory here. We look at the equation in the differential form, m dx and dy equals 0. So we check for exact equation by looking at partial m partial y equals to partial n partial x. If they're the same, then the equation is exact. If they're not the same, the equation is not exact. If yes, meaning that the equation is exact, then we find a function psi such that partial psi partial x is m and partial psi partial y equals to n. Now, please be careful when you write out the partial derivative. For checking exact equation, we look at partial m partial y and partial n partial x. But when we find the function sign, we need to look for partial psi partial x equal to m and partial psi partial y equal to n. So the derivative, the partial derivative is different here. Once we have found the function sign, which is called the potential function, then the equation, then the ODE can be written as a total differential d psi equal to 0. And this implies that psi equal to a constant c. And we obtain here our general solution to the ODE. And if we are given initial condition, we can use those values of x and y to determine c. So let's look at some examples of how we solve certain equation. Solve the ODE. Y prime equals to cosine y minus 2e to the 2x divided by x sine of y. There is no initial condition here, so we solve for general solution. So first, we need to rewrite the equation in the format m dx plus n dy equals 0. This is the differential form format. So to do so, we replace y prime here as usual by dy dx. And then we cross multiply and move things to the left hand side. By cross multiplying, we will have x sine y dy equal to cosine y minus 2e to the 2x dx. And now we're gonna move one side to the other, either way. So I'm gonna rewrite as let's move this right hand side to the left, so it becomes minus cosine y plus 2e to the 2x. When I move this to the left, I need to change the sign, and then plus x sine y dy equals 0. And now I have the correct format for the differential form of the equation. So m dx, m is the whole thing here, and n dy, and dy, the whole thing there. So m is minus cosine y plus 2e to the 2x, and n is x sine y. Now let's check whether the equation is exact or not. Check for exact equation. So we compute partial m partial y. Derivative of this with respect to y. So x is a constant. When we take the derivative in the y, we have sine of y, and partial n partial x. Derivative of this in the variable x, and y is a constant, so we just have sine of y. We see that the two are the same. So the equation is exact. Once the equation is exact, we can go ahead and find the potential function, find psi, such that partial psi partial x is our m, which is way up here, minus cosine y plus 2e to the 2x, minus cosine y plus 2e to the 2x. And another equation for psi partial y is n, which is right x sine y. I usually label the equation here as equation 1 and the second one equation 2. We need to determine a function psi satisfying these two conditions. Now, if possible, you can guess what psi is. Yes. If you can do that, it's good. But if you cannot guess, then here is a systematic way to solve for psi. Look at the first equation, equation 1. It says that partial psi partial x is whatever on the right hand side here. So we could integrate equation 1 in x, in the variable x, and I will have psi is the integral of minus cosine y plus 2e to the 2x dx. Now when we integrate in the variable x here, we are thinking of y as a constant. So this is just, you can say that this is a partial integral. So integral in x, we would have minus x cosine y plus integral in x of this will be e to the 2x plus a constant. However, constant here, because we're taking antiderivative in x and we're keeping y as a constant, so the constant will depend on y. Because of that reason, I will denote this by h of y. This is a constant, but it depends on y. So that's how we use the first equation. Now to use the second equation here, I'm not gonna integrate again, but instead I will take the derivative. This equation 2 says that partial derivative of psi in y should be x sine y, and And now I already know what psi is, right? After integrating in x, I have the format, I have the formula for psi. So this implies that partial psi, partial y, if I take the derivative in y, I would have minus x times minus psi y, which simplified to x psi y plus the derivative of e to 2x in the variable y would be 0. And over here, I have dh dy, because when I take the derivative of a function in y, I just have that, the h dy. Now, I'm gonna equate this with the right-hand side of equation 2. Equation 2 says partial psi partial y is the same as x psi y. But I have computed partial psi partial y as this. So I need to equate x psi y plus dh dy with the right hand side of equation 2, which is x psi y. And now I can solve for h. I see that these two are the same, cancel out. So dh dy is 0. So h will be the integral of 0 in the variable y. And now I will have a constant. But I will not need to add a constant right here. Plus constant. But we may ignore right now, for now. So we have found our potential function psi as, go back here, psi is minus x cos psi y plus e to 2x plus h of y. And we found below that h of y could be taken to be 0. So psi is just minus x cos psi y plus e to the 2x. Then our ODE can be written as a total differential d of minus x cos psi y plus e to the 2x equals c. And whenever the total differential equals 0, the function equal to a constant c. And this gives a general solution to our ODE. Now for this general solution, we could actually solve and get the implicit and get the explicit solution. But it's okay to leave it in this format. This is implicit solution format. Alright, so let's look at another example of how to solve such a differential equation. In this case, we will have an initial condition. So we'll have initial value problem. The equation is given as y prime equals to minus 2x e to the y squared divided by 2x squared y e to the y squared minus 3 and y0 equal to negative 1. As before, the first one is our ODE and the second one is our initial condition. So to solve this equation, we need to rewrite in the differential form. M dx plus n dy equals 0. To do so, we think of y prime as the ratio dy dx. And we cross multiply. We get that on this side, on the left side, we have 2x squared y e to the y squared minus 3 in parentheses dy equals to minus 2x e to the y squared dx. And we need to move everything to one side. And move this term to the left and change the minus sign to a plus sign. So always write the term with dx first. So we have 2x e to the y squared dx plus 2x squared y e to the y squared minus 3 dy equals 0. And now I have matching the format m dx plus n dy equals 0. So we see that m is that and n in the second term. M is 2x e to the y squared, and n is 2x squared y e to the y squared minus 3. Now let's check for exact equation. We need to look for partial m, partial y. Taking the derivative of this in terms of y, and we keep x as a constant. We need to use the chain rule here. To x as a constant, and then we have the derivative of e to the y squared in the variable y. So by the chain rule, we have e to the y squared times 2y. And then partial n, partial x. Y is a constant in this case. So the derivative 2x squared will give us 4x. And y e to the y squared is considered constant. The derivative negative 3 is 0. And now looking at the two partial derivatives, the first one actually simplified to the same thing as the second one. So 2 times 2 is 4, and then I just rewrite xy e to the y squared. The two things here are the same. So the equation is exact. Now we need to find the potential function by psi, such that we have two equations. Partial psi, partial x should be m, which is 2x e to the y square. This is our equation 1. And then partial psi, partial y should be n, which is right here, 2x squared y e to the y squared minus 3. 2x squared y e to the y squared minus 3. Equation 2. As before, if you can guess what psi is, then you can write down the formula for it. Otherwise, there's a systematic way to do it. Integrate equation 1 in the x variable. Then we will have psi is the integral of 2x e to the y squared dx. And we get x squared e to the y squared plus a constant. But as before, the constant here depends on y. So we denote it by h of y. Then we take partial derivative of psi in y to equate with the right hand side of equation 2. Partial derivative in y, we have x squared, and derivative e to the y squared in y, we have e to the y squared 2y plus dh dy here. And we need to equate this with the right hand side of equation 2. So what do we get? We have x squared here, and e to the y squared times 2y plus dh dy equals to right hand side of equation 2, which is exactly the same as n, and we have 2x squared y, 2x squared y e to the y squared minus 3. For now, we're going to solve for h. But you see that the first terms on both sides cancel out. We get dh dy equal to negative 3. Now we solve for h by integrating negative 3 in the variable y. We get minus 3y plus a constant, but no need to do that here. So put everything together, we have found our potential function psi is going back right here. Our potential function psi has a format x squared e to the y squared plus h of y. But h of y is what? H of y is negative 3y. So together, we have x squared e to the y squared minus 3y. This is the potential function psi. And so our ODE can be written as a total differential of x squared e to the y squared minus 3 equal to 0. And so x squared e to the y squared minus 3y equal to a constant, which is the general solution. But we are given initial condition y0 equal to -1, meaning that when x equals 0, y equals to -1. Plug these values in, we have 0 e to the 1 minus 3 times -1 equal to c. From here, we see that c is positive 3. Now we plug c equal to 3 back in. We have x squared e to the y squared minus 3 equal to 3. This is our equation, our solution to the equation, implicit solution. To the given equation. For this, we won't be able to solve for y, so we have to leave the solution in the implicit form. Now, what happens if we have an equation which is not exact? What can we do? If the equation is not exact, we won't be able to find the potential function psi. So it turns out that for some equations, if they're not exact, we can find an integrating factor to multiply the equation through by that integrating factor, and then the equation becomes exact. From there, we can continue solving. That will be given in a different lecture.